Hello guys, and welcome back to Introduction to Number Theory. Now I will try to prove that all elements can be decomposed into prime factors, and I think I'll manage to prove this. First of all, let me remind you that prime elements and indecomposable elements mean the same. Then let's just take any element and try to decompose it into prime factors. Say, let n be just an element of our Euclidean ring. Then it's either prime itself, which means indecomposable, which means that we already have the needed decomposition, or it is not prime, which means compound, which means decomposable, which means that it can be represented as product of two other elements, each of which is in some sort less than n, which means that both A and B are irreversible, which means that they are not units in our Euclidean ring. Then we can take a look at A and B, and they might both be prime. In that case, we already have decomposition, but they might not be prime. And in this case, we'll say if B is not prime, we can continue to decompose N and say that A multiplied by X and Y, where X and Y is a way to decompose B if it is not prime. Then we can take a look at these three factors, and if all of them are prime, then we have the decomposition, and if not, we can continue this, and so on and so on. And the main question is, will this ever end? I mean, could it be that we can, with this process of decomposition is infinite? Well, in Euclidean ring, this is not possible, and now I'll explain why. First of all, notice that when we decompose an element into product of two other elements, both of which are irreversible, then the norm of the element on the left-hand side is strictly greater than both norms A and B. At the same time, we know that the norm of an element is a non-negative integer, so it can have not so many different values. And we can use this to prove that our algorithm of decomposition will come to an end at some time. But how do we use it? Well, as usually, when we have some non-negative integer value, then we can use the induction method. So let us now try to conduct this induction on the norm of the element which we try to decompose. As we all know, induction consists of two parts. We have the base of induction, where we take some small values of induction value, induction parameter, and prove that it holds for the small values. And the second part is where we have this induction hypothesis and use it to prove in general case. So base of induction might consist of some small value of norm n. We'll say if norm of n is equal to, for instance, 0, which is the least possible value of norm, then it is rather obvious that n cannot be decomposed into two elements, none of which is irreversible. The base of induction is, as usually, simple. Now let's go to the step of induction, and suppose that for every m such that norm m is less than norm of n, for every such m there exists decomposition of m into prime factors. Now we say nothing about the uniqueness of this decomposition. All we are concerned about is whether this decomposition exists or not. So we suppose that for every m such that norm of m is strictly less than the norm of m, we suppose that such decomposition exists. Well, let me write here that we only have in mind prime decomposition of m into prime factors. Now, take a look at them. So this is an induction hypothesis. Let me get it into a frame. This is the hypothesis. And now let's take a look at them. Well, it's, as I said in the beginning, it's either prime, then we also have decomposition, or it can be represented as a product of two other elements, both of which have norm which is strictly less than the norm of n. And at this very moment, when we can apply the induction hypothesis and say that both A and B have their own decomposition. Say let A be equal to A1 multiplied by A2 multiplied by and so on multiplied by AL, where all these elements are prime, and also B has its own decomposition into prime factors, where all of these B1, B2 and so on, Bk are prime. So we simply take these two decompositions, put them into this expression here, and we gain that n is equal to product of all these prime elements, which means that n also has a decomposition into prime factor. This way, we proved that any element of a Euclidean ring indeed has a decomposition into prime factors. I remind you that now, by this time, we do not know whether this decomposition is unique or not. It is a different question, but it certainly exists.